Hey, how's everyone doing today? Good to hear, man. Good to hear. Pretty good, pretty good. Kind of a dreary day outside, but who goes outside anymore? Am I right? All right. So, let's get rolling. Okay. So today we're gonna finish up talking about cylindrical coordinates and integration of cylindrical coordinates, and then hopefully we can start talking about spherical coordinates. But let's remind ourselves what's going on here. So just want to emphasize, the whole reason we're doing these other coordinate systems is because we're going to want to integrate over different shaped regions, either in R3 or in R2. So in R2, if we have regions bounded by, circles or pieces of circles, those are generally much easier to describe in polar coordinates. Similarly, we have cylindrical and spherical coordinates in R3 to describe regions of different types, and it makes integration much cleaner over those types of regions. So for cylindrical coordinates, the types of regions that are best described by cylindrical coordinates are going to be those with radial symmetry. So best for integrating over regions in R3. So in space, over regions that have radial symmetry or are pieces of regions with radial symmetry. So in other words, symmetry about an axis. Sometimes we won't do the entire thing. So like the actual region won't be radially symmetric, but if you sort of like take the entire thing, so like we could take like a piece of a cylinder, like half a cylinder or something like that. The entire cylinder itself is going to be radially symmetric. But yeah, so for instance, it's going to be symmetrical about the z-axis in this case, but we can actually use cylindrical coordinates about other axes. Yeah. So cylinders, right? You have a cylinder. It's symmetrical about the z-axis, right? You have an axis of, you basically rotate something about the z-axis and you get your cylinder. So your cylinders, your cones, like sometimes elliptic paraboloids. These types of regions. Mostly cylinders, though, are generally what we see. Sometimes cones, but yeah. So your cones, or your half cones, generally. So you just take your slanted line and you rotate it about the z-axis. That's radial symmetry there. And then sometimes we might see elliptic paraboloids. Whoops. you take your parabola and you rotate it about the z-axis, and you get an elliptic paraboloid. So it's these types of regions bounded by this sort of stuff. And I want to emphasize that. That's where cylindrical coordinates really shine in this case. Okay. So just a reminder. So for cylindrical coordinates, let me give myself more room here. So for cylindrical coordinates, we describe a point using r, theta, and z. That's going to be the ordered triple we use for cylindrical coordinates. So z is going to be, so suppose in rectangular coordinates, we call this guy x, y, z. So z is going to be the usual z, right? The distance along the z-axis, the height. And x and y work like they do in polar coordinates, except, so take your point, project to the xy plane. So take z to 0, keep x and y the same. Hang on, that's kind of a bad picture there. Okay, so z is the same. Project your point down to the xy plane, and r and theta are the same as they are in polar. Theta is the angle measured counterclockwise from the positive x-axis. And r is the distance of the projection to the origin. But another way of thinking about it is the distance to the z-axis. So that distance is the same as this distance here. If you take your point and you look at how far away from the z-axis it is, that's going to be r. Or alternately, think of r and theta the same way as in polar, right? Project down to the xy plane, and then you're just in r2, and then r and theta work the same way. So theta, think about the angle. So think about rotating about the z-axis. So taking your point, so if you start it above or below the positive x-axis, so it's the angle measured counterclockwise from the positive x-axis. And so think of just starting at the positive x-axis, everything directly above and below the positive x-axis, the angle theta is 0, right? And then as you're increasing your angle, you're going around the positive z-axis. You're just taking this point and you're rotating it about the positive z-axis counterclockwise. So until you get back around to 2 pi, and then you're back on the positive x-axis. So on the positive x-axis, directly above or below, your angle 0. And then as it increases, you're rotating counterclockwise around the positive z-axis until you get back around. So that's how I like to think about theta, is angle about the positive z-axis. Or if you project your point down to the xy plane, it's the normal theta. So any confusion about that point? Because there's often some confusion with theta, and then we'll see later with phi when we talk about spherical. But I find that's the best way to think about theta. Right, so let me see. So suppose this point is directly above the x-axis, right? Your theta is going to be 0 for that point. So if we keep the same r, the same distance from the z-axis, and the same z, the same height, but we change theta to say pi over 2, now it's lying directly above, pretend that's lying directly above the y-axis. Let me do a better job about that. The positive y-axis. So suppose this is, sorry, hang on. R0 z. So we fix an r, we fix a z. When theta equals 0, you're directly above the x-axis. When theta equals pi over 2, you're directly above the y-axis. When theta equals pi, you're directly above the positive z, or the negative x-axis, sorry. And then when theta equals 3 pi over 2, sorry, that's a really terrible picture. Directly above the negative y-axis, and then theta equals 2 pi, you've gone all the way around. So you're just taking your point, keeping the same height, keeping the same distance from the z-axis, but rotating about the z-axis. Okay. So, sorry, we have, don't want to spend too long on here. Yes. And in fact, let me just do this on here. So we have the relationships z equals z. And then the same polar relationships we had. X is r cos theta. Y is r sine theta. And x squared plus y squared is r squared. So the x and y relationships are the same as in polar, because r and theta are the same as in polar when you project down to the y-axis, xy plane, sorry. Okay. So just the main thing you should remember is r equals a constant. So r equals r naught. In polar, or in cylindrical, this is going to describe the set of all points which are distance r naught from the z-axis. So that's going to be a cylinder centered about the z-axis of radius r naught. That's the main thing to remember. The rest you can kind of figure out with using those relationships. X is r cos theta, y is r sine theta, x squared plus y squared is r squared. Okay. So here's how we're going to integrate. in cylindrical coordinates. So suppose the region W, in cylindrical coordinates, we could describe it as a set of all points r theta z such that so z is going to lie between z1 of r theta and z2 of r theta. Hang on, let me erase this and then draw a picture here. Better yet, yeah, this is fine. We'll just do some examples and it'll become clear. So z is going to be bounded by z1 of r theta, z2 of r theta. Think of this as a top and a bottom surface. And these guys are going to be radially symmetric. Usually it's going to be like a plane or a cone or that kind of thing. So z lies between z1 of r theta, z2 of r theta, r. Usually r is just going to lie between numbers, but it could also lie between functions of theta. Just think about r lying between numbers. So basically, if you take your thing, you integrate with respect to z, you're pushing it down to the xy plane. When you do that, when you collapse it down to the xy plane, then you get a nice polar figure, right? Something bounded by like circles, pieces of circles. And then we can describe that using polar coordinates. And then theta is going to lie between, say, theta 1 and theta 2, between two numbers. So if this is our W, our region W we're integrating over, we're going to integrate with respect to Z first. We're always going to integrate with respect to Z first when we do cylindrical. Well, hang on, let me write this out. So we're integrating a function f of x, y, z over such a region W, where we can use cylindrical coordinates to describe this nicely. So the way we do that is we do what we did with polar. We change x, y, and z to their cylindrical equivalents. So x becomes our cos theta, y becomes our sine theta, z stays z. So just go to your function, replace x with our cos theta, y with our sine theta, z with z. And dv becomes r dz dr d theta. So remember, in polar, dA becomes r dr d theta. You need to have that memorized. In cylindrical, cylindrical is basically z. You integrate with respect to z and then go down to the xy plane, and then it's polar. So it's dz and then go down and do polar, then it's r dr d theta. So you need to multiply your entire function by r here. And then, of course, z goes from z1 of r theta up to z2 of r theta. really hard to write small here. My apologies. R goes from R1 of theta, usually just a number, up to R2 of theta, usually just a number. And theta goes from theta 1 to theta 2. Okay, well, we'll talk more about what I mean by this, but here's how you want to think about the bounds for cylindrical. Right, so you're going to integrate with respect to Z. You're going to find the bounds, the top and bottom bounds, switching to polar, and then you're going to project down to the XY plane, and then you're going to have some polar region, and then you use polar coordinates to find the bounds for R and theta in the XY plane. But that's how you want to be thinking about cylindrical. But yeah, converting to cylindrical, exactly like converting integrals to polar, replace x, y, and z with their equivalent in cylindrical, and then dv becomes r dz dr d theta. Okay, so for example, let's calculate the integral. I'm mostly going to spend time setting these up, and then I'll really power through the calculations or not do them at all, because those are not the important parts. So the integral over the region W of z square root x squared plus y squared with respect to volume. We're here. W is going to be the region. So it's going to be the region. So here, x squared plus y squared is going to be less than or equal to 4. And then z is going to lie between 1 and 5. So let's do a quick, really rough sketch. So I like to sort of, so you don't have to sketch like exactly what this looks like, because often, so for instance, we'll see in this, I'll explain as we go along. So we have x squared plus y squared less than or equal to 4. So what is x squared plus y squared equals 4? What surface does that describe in R3? So that's what it would be in R2, right? But what about in R3, right? It's a cylinder. It's just the cylindrical surface of radius 2 centered on the z-axis, right? And so z goes from z equals 5 up to z equals 1. And that cylinder is x squared plus y squared equals 4. So we can think of x squared plus y squared equals r squared. Well, sorry. Yeah, that's fine. R, where R is like the radius of your cylinder. As that number shrinks, right, because we're doing x squared plus y squared less than or equal to 4. So as that number shrinks, your radius shrinks and you're just shrinking into the positive z axis. So we're looking at everything inside of that cylinder. So x squared plus y squared less than or equal to 4 means everything inside of the cylinder, x squared plus y squared equals 4. Does everyone understand that bit? And then z goes from 1 to 5. So the bottom surface is z equals 1, a plane, and the top surface is z equals 5. Does everyone see this is the region W we're talking about? Okay. So let's convert to cylindrical coordinates because this is a nice region with radial symmetry. It's bounded by a cylinder and planes, right? That is a classical region where cylindrical coordinates is useful. I mean, it's got the name in there, cylinder. Okay, so first, let's find the bounds for z, and then project down to the xy plane, and then find the bounds for r and theta, like we do for polar. That's how I like to do these. Okay, so z. Z is easy. We're given the bounds for z, right? Z is bounded below by z equals 1 and above by z equals 5. Easy enough. If, say, z were bounded above by, say, say z equals x, like some slanted plane, then we would have to change that to cylindrical coordinates, right? You can't have x in your bounds because x is not a variable in cylindrical coordinates. So x would have to become r cos theta, right? Right, so the equation you need to change to cylindrical if necessary. But in this case, we don't need to because they're just numbers. Okay, so then for r and theta, we're going to project down to the xy plane. When we do that, so we see we just have the circle x squared plus y squared equals 4. And everything inside of there. And so let me draw this down here. Oh, come on, dude. So for this region in polar, r is going to go from what to what? So remember, if the origin is in your figure in polar, r is bounded below by 0, right? So the origin's in there, 0 is automatically the lower bound. And then you draw your line out from the origin and see the outer curve that this hits. Well, the outer curve is what? R equals what? R equals 2, right? And then theta goes from what to what? 0 to 2 pi, right? We get the entire circle, right? We're going all the way around the origin. If we only got like the top half, it'd be like 0 to pi, etc. But we go all the way around, so it's 0 to 2 pi. Okay, so we got our bounds. Let's write out our integral. Okay, so z square root x squared plus y squared, we need to convert this to cylindrical. So wherever we see z, we replace it with z. Why isn't r from -2 to 2? It's because r is not, so think of r as distance to the origin, right? R equals -2 doesn't make sense in that case. So always think just r as positive is the way you want to do it there. So yeah, like I said, let me just emphasize this. So I like to draw a line starting from the origin. Oh, come on, dude. Why are you like this? All right. A line starting at the origin through the figure. Look at the set of points, the curve, which is closest to the origin. In this case, the origin's in there, so 0 is the lower bound. And then look at the curve furthest away, right? So the outer boundary curve. And that's this outer curve here. And so the equation of that is r equals 2, because it's x squared plus y squared equals 4, r squared equals 4. We always take r positive, r is 2. And so r goes from 0 to 2 in that case. That's how I like to think of it. Okay. So let's convert z squared x squared plus y squared into cylindrical. Z stays z. What is the square root of x squared plus y squared in cylindrical? So x squared plus y squared is what? Remember, it's the same as polar. X squared plus y squared is r squared. So square root r squared is just r. That's what our function becomes. And then dv becomes r dz dr d theta. Can't forget the r. You have to multiply the whole thing by that. Z goes from 0 to 2, we said. R goes from, nope, sorry. It's R. Z goes from 1 to 5. R goes from 0 to 2. Theta goes from 0 to 2 pi. And let's just multiply the entire thing through by r. So we get zr squared dz dr d theta. Really quickly. So let's just do the first integral. Zr squared with respect to z. What do we get when we integrate zr squared with respect to z?
Z squared r squared over 2.
Right. So r is just a constant because we're integrating with respect to z. Z becomes 1/2 z squared. So you get 1/2 z squared r squared evaluated from z equals 1 up to z equals 5. So you can pull out the 1/2 r squared because it's a constant here. And then z squared at 5 is 25. Z squared at 1 is 1. So we get 1/2 r squared times 24, which is 12r squared. And then we plug that in and we know how to do the rest. if you want to do this integral yourself, which I would suggest you do, we get 64 pi at the end. The important thing is setting this up, getting the proper bounds, converting your integral to cylindrical properly.
I forgot what you said. Were you saying that like on the exam that you actually want us to like solve the integrals, or do you want us to just?
It depends on the problem. We're always going to have some problems where we ask you to evaluate the entire integral. Sometimes, in the interest of time, just so we can get to more material, we'll just ask you to set up the integral. But even on the problems where we do ask you to evaluate the integral, the actually setting it up before you do any evaluation is going to be the bulk of the points. But you do need to know how to evaluate integrals, obviously. Okay. So in the interest of time, let's do this example here. So this one, we're just going to set up an integral. So we're going to take an integral along with the bounds in rectangular and convert it to an integral in cylindrical. Okay. So you have the integral from y goes from -1 to 1, x goes from 0, square root 1 minus y squared. Z goes from x squared plus y squared up to square root x squared plus y squared. And the integrand is xyz. So then that's dz, dx, dy. Okay, so what we're going to want to do is to sketch this, but you can save yourself a lot of time. So you want to sketch and then find the bounds. But you can save yourself a lot of time by forgetting about z, essentially, because z is really easy. So we're integrating with respect to z first. In cylindrical, you can just directly take the x squared plus y squared, change it to cylindrical, and the square root x squared plus y squared, change it to cylindrical. And then you got the bounds for z. Boom, you're done. You don't need to do anything else there. Then you want to focus on what's going on in x and y. So that's taking it, projecting it down to the xy plane, and then find bounds for r and theta. So you don't need to draw what's going on in 3 dimensions. You just need to see what happens to z. You can directly plug in the bounds. It's nice. And then look at x and y, and then do that in polar to find the bounds in r and theta. Okay. So let's do z. So z is bounded below by x squared plus y squared. What is x squared plus y squared in cylindrical? We just did this. R squared, right? So x squared plus y squared is r squared, and then bounded above by the square root of x squared plus y squared, which is square root of r squared, which is just r. So these are our bounds for z. Easy. Don't need to sketch that in 3 dimensions. It's that straightforward. Then we forget about z and look at the bounds for x and y. So project down to the xy plane. Okay, so first, let me wall this off here. So we have the bounds for x. X goes from 0, I'll just write it out, to square root 1 minus y squared. Y goes from -1 to 1. Okay, so let's look at x. So the left bound is x equals 0, which is the y-axis. And the right bound is x equals square root 1 minus y squared. What is x equals square root 1 minus y squared? How would you describe that? Right, it's the right half of the circle x squared plus y squared equals 1, right? So if you get x by itself, you get x equals plus or minus square root 1 minus y squared. And we're looking at the positive part where x is positive. So the right half of that. Okay. So that's the left and right bounds. But depending on what y is, we may not get the entire right half of the circle or the disk. So if y goes from, say, 0 to 1, we'd only get like this bit up here, the top half. And so which part we get depends on what happens with y. But y goes from -1 to 1. And so we get the entire right half of the circle. Does everyone see that? So if y had gone from 0 to 1, we'd only get like the top half, or from like -1 to 0, we'd get the bottom half. But it goes from -1 to 1, so we get the entire right half of the disk. And I want to emphasize, you need to sketch this because you can't get the bounds directly from just like plugging in stuff in polar in here. It doesn't quite work like that. Okay, so we get the right half of the disk of radius 1 centered at the origin. So r is going to go from what to what?
Zero to 1.
Right, so the origin's in there, so r is bounded below by 0. And we go out to the circle of radius 1, which is r equals 1. So r goes from 0 to 1. And theta goes from what to what? So we start down here, which is -pi/2. And we go up to pi/2. Right, remember, you want to have a continuous interval for theta going counterclockwise. So figure out where you start and then go counterclockwise to where you end, right? So if you wanted to call this guy 3 pi over 2 down here, you'd have to be increasing theta until you hit the top, which would be 5 pi over 2. It's easiest just to do negative pi over 2 to pi over 2. Okay, so let's write down our integral. Okay, so we have x, y, z is the integrand. So we need to change that to cylindrical. X becomes r cos theta. Y becomes r sine theta. And then z is still z. dv, well, okay, so dz dx dy is our dv in rectangular. So when we convert to cylindrical, the dv is r dz dr d theta. So does everyone understand that bit? dv, when you're doing cylindrical, it's just dz dx dy or whatever order you want to do it in. Or when you're doing rectangular. In cylindrical, it's r dz dr d theta. And then we have, okay, z first. Z goes from r squared up to r. R, we said, goes from 0 to 1. And theta goes from negative pi over 2 to pi over 2. So just multiplying everything through, you know, let me not even do that. If we wanted to evaluate, which we're not going to do, but if we wanted to evaluate, just multiply everything through. So we get r times r times r, so we get r cubed, cos theta, sine theta, times z. Or let me just say like r cubed z, just so we don't, yeah, whatever. And then we'd integrate, as usual. But as always, the important thing, being able to get the bounds. That's always the hardest part and the most important part, right? So think of the bounds as finding the bounds for z, and then collapsing down to the xy plane, and then using polar to find r and theta. Okay. Any questions about this? Okay, so that's it for cylindrical. Tomorrow we will look at spherical coordinates and how to integrate in spherical. So yeah, have a good rest of your day, and I will see you all tomorrow.